Today we will be starting, essentially, trig proofs. Starts with fundamental identities. This box here, we should already know all these things. These are the reciprocal identities. It says sine of theta and cosecant theta are see, I almost screwed it up, are reciprocals of one another. Sine of theta is 1 over cosecant theta. Cosecant theta is 1 over sine theta. Secant theta and man, I'm struggling. Secant theta and cosine theta are reciprocals of one another. Cosine theta is 1 over secant theta. Secant theta is 1 over cosine theta. Tangent theta and cotangent theta are reciprocals of one another. So tangent theta is 1 divided by cotangent theta, and cotangent theta is 1 divided by tangent theta. Tangent and cotangent, though, are both fractions. Tangent of theta, like we've seen in the past, is sine theta over cosine theta. So its reciprocal then, cotangent theta, is cosine theta over sine theta, or x's, whatever you want to use. Okay, all that stuff, we've already done all of that. And we've actually already done the even-odd identities as we were learning about sine, cosine, and tangent, and then later on their reciprocals. We did talk about the symmetries that these functions have. Basically, cosine is an even function because it is symmetric around the y-axis. And since cosine is an even function, so is its reciprocal, secant theta. Those are the only two trig functions that are even. So all the other ones are odd. What does it mean to be even? It means that making the angle negative is essentially the same as doing absolutely nothing, which is what you're seeing in these two statements. Whereas all the other trig functions are odd. Odd functions have the property where if you make the angle negative, it was the same thing as if you had made the entire function negative. So reflecting over the y-axis is the same as reflecting over the x-axis. Useful stuff. Now here we have the Pythagorean identities. This right here is the trigonometric identity. It is the most important trig identity there is. Second period said that we haven't talked about this yet this year. So what we're going to do is we're going to come down to example 1, and we're going to see why the Pythagorean identity is true. Here, I have quadrant 1 of the unit circle. So when we draw this hypotenuse of our triangle, it will be equal to the radius of that circle. Now, I said it's the unit circle, so how long is that radius? 1. Yay! Right there. This will be our theta, because it's in standard position. This is x, this is y. We have a coordinate here of x comma y on the unit circle. So somewhere around that circle. Because this is a right triangle, it's going to have to follow the Pythagorean theorem. X squared plus y squared, or a squared plus b squared equals c squared, right? A squared plus b squared equals c squared. That means x squared plus y squared equals 1 squared, which is 1. That happens to be the equation of the unit circle, centered at 0, 0 with a radius of 1. Now, what we've learned so far in trigonometry, though, allows us to make a substitution. Remember, cosine of theta is x over r. But in the unit circle, what is r? It's 1. So cosine of theta is x over 1. That means cosine of theta is literally equal to the x value in the unit circle. And we can use the same logic for sine theta. Sine theta is y over r, but since we're in the unit circle, r is 1. So sine of theta is just equal to y. So if we take what x equals and take what y equals and substitute them into this formula, what we get is x squared would have been cosine squared theta. Cosine of theta, quantity squared, looks like this. That means take whatever cosine of theta equals and then square that result. That's what that means. This is, right here, this means this. But mathematicians don't like to write all the extra symbols, so they write it like that. Just so you know, that's what that means. And y, being sine of theta, squared gets us this. So there we have the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. And of course, the order of addition doesn't matter. So sine squared theta plus cosine squared theta equals 1. Yes, Adi? Why would you write all of this out? Because this relates the trigonometry to each other, whereas this is x's and y's in the xy coordinate system. But there are other coordinate systems other than x comma y. This is called rectangular coordinates. There is an entire coordinate system called polar coordinates, which uses r's and thetas instead of x's and y's. And your graph paper isn't little rectangles, your graph paper is actually circles. And that's why. Now, this one identity gives me the ability to write not a function, an identity for cosine squared theta or for sine squared theta using simple arithmetic. If I wanted to get sine squared theta alone, all I'd have to do is subtract cosine squared theta from both sides, right? Yeah. So as it turns out, sine squared theta equals 1 minus cosine squared theta. That's just arithmetic. Subtract cosine squared theta from both sides. Or, say you wanted to get cosine squared theta alone. Fine. Subtract sine squared theta from both sides. There. There are 3 identities on the paper. This one is true because of the Pythagorean theorem. These 2 are true because of arithmetic from this. Cool? So right now, I have an identity for 2 of the trig functions, don't I? Squared. Wouldn't it be nice if there was an identity that, there were identities, I should say, for all of the trig functions? There's 2 of them. 2 down, 4 to go, right? All right. Which one do you guys want next? Tangent. You want to do tangent? Fine, let's get tangent. Let's get one for tangent squared theta. What does tangent of theta equal? Y over x, but in functions is sine over cosine. Oh. Well, here I have a sine. So if I were to divide by cosine squared theta here, this would say tangent squared theta. So what I'll do is I'll take my cosine squared theta plus sine squared theta equals 1, and I'll divide everything by cosine squared theta. Because that is going to give me a tangent squared theta right there. Cosine squared theta over cosine squared theta is 1. Sine squared theta over cosine squared theta is tangent squared theta. And 1 over cosine squared theta is secant squared theta. Oh, look! There is the Pythagorean identity that isolates secant squared theta. Jack said he wanted tangent squared theta. Fine. Subtract 1 from both sides. There. 4 down, 2 to go. Well, here we divided everything by cosine squared theta. How about instead of dividing by cosine squared theta, you divide by sine squared theta? Well, cosine theta over sine theta is cotangent theta. So this is going to give me cotangent squared theta. Sine squared theta divided by sine squared theta is 1. And 1 over sine squared theta is cosecant squared theta. There. We've isolated cosecant squared theta. You want to isolate cotangent squared theta? Subtract 1 from both sides. Ta-da. Here are 7 different these 6 purple ones and this one in blue, Pythagorean identities. They are all true because a squared plus b squared equals c squared. We just derived all 7 of those. So could you commit them all to memory? Yes, you could. Do I have them all memorized? Nope. Sure don't. No shame in my game. You know what I have memorized? This one blue one, because it is the identity, and then these 2 right here. Because by accident of using them a billion frigging times, I have these 2 memorized. But these 4, nope. I don't have them memorized. I build them when I need them. I know where they come from. Is that slower than having them memorized? Sure is. And does that mean that there's times where I have to do extra work because I go, I wonder if that was a Pythagorean identity for tangent squared theta. So I go through the process of building the Pythagorean identity for tangent squared theta. It turns out it wasn't. And I go, oh, okay, well, that wasn't it. Moving on. It happens. But my memory is garbage. So no, I don't have these 4 memorized. I know how to get them if I need them. These 2, accidental memory. Something that may or may not be useful to you, I don't know yet, is, if you're looking here, 1 minus cosine squared theta, 1 minus sine squared theta, secant squared theta minus 1, cosecant squared theta minus 1. Those 4 things all have something in common. Well, all the Pythagorean identities do have a 1 in them somewhere. But specifically, this one, this one, this one, and this one have something in common. They're all the difference of 2 squares. So this one, this one, this one, and this one will all factor to a plus b times a minus b. Sine squared theta equals 1 plus cosine theta times 1 minus cosine theta. Cosine squared theta is 1 plus sine theta times 1 minus sine theta, so on and so forth. Because a squared minus b squared always factors to a plus b times a minus b into a set of conjugates. So these 4 are the difference of 2 squares. Isn't that nice? And that knowledge is useful sometimes. Ready to try some things? All right. We are identifying, well, it says use a quotient identifier to simplify and rewrite. Here's what we're doing. We're confirming that this is a true statement. That's what we're doing. By the way, that symbol is beta, in case you don't know. Greek letter beta. Or you could say it is the German letter S set, whatever you want to call it. But we'll call it beta because we use Greek letters for angles. Shh. Psst. We are confirming that this is a truth. Let me tell you what you are never allowed to do when you are proving something is true. You are never allowed to assume it's true. And what does that mean? That means you are not allowed to perform an operation on both sides of this equation. I can't add 1 to both sides. I can't square both sides. Not allowed to do that. Because the only way you're allowed to do that is if you know it's a true statement already. And since we're trying to prove that it's true, we are not allowed to assume it's true. For example, you looked at me and you said, prove to me that this pen is purple. And I said, okay, first let's assume this pen is purple. And since it's purple, it's a true statement, it's purple. There, I win. You see, you can never assume something is true when you're trying to prove it is true. You're looking at me like I'm crazy.
Do we have a couple things that we can say are true?
No.
Nothing?
There is a very small set number of things in mathematics that we have to say are just true and unprovable. We call them postulates or axioms. We have them in geometry. I don't know if you remember the postulates from geometry. There's a set number, I think it's 12 things that are called axioms as well, that we just say, these are true, they must be accepted.
So I couldn't say that the color of the pen is a mix of red and blue.
No, can't do that. No. But you could say to me, prove that 1 plus 0 equals 1. That can be proven using logic and not assuming it's true. Okay? So here we go. This is a true statement, but it is our job to prove it is true. So how do we prove things are true? Well, you have a question for me? Okay. There's a couple different ways that we can prove things are true. First way you could do it is work on one side, doing things to this one side that are true until it equals the other side. You can do that. So you can do a bunch of crap on the left until you get the right side. And when you do get the right side, congratulations, you proved it's true. Or you could do a bunch of stuff to the right side. Just things that you know you're allowed to do to something, like using equalities, right? Like I could multiply this by cosine beta over cosine beta. Why? Because cosine beta over cosine beta is 1. It's not something that needs to be done to both sides. So you could work on the right side until you get the left side. Congratulations, you've proven it's true. Or you could work the two sides independent of one another, and if ever you get a statement where the left side equaled the right side, then you're done. So you can either show that the left equals the right, or you could show the right equals the left, or you could work the two sides independent of one another to show they both equal the same thing. Okay? I am going to go from the left, and I'm going to do only stuff on the left, and eventually I'm going to end up on the right side. How so? Well, I know that tangent of beta happens to be sine of beta over cosine beta. And cosine beta over cosine beta is 1, so I'm left with sine beta. Done. I used one identity and simplified, and I ended up with what was on the right side. Finished. We've proven that these are true, that these are the same thing. That's as simplistic as it gets. Bless you. Here, what do we see? Again, I'm going to go from left to right. What do I see? I see a reciprocal function. And I know that secant of x is actually 1 over cosine of x. There, I ended up on the right side. Ta-da. Now, what I was doing in my first period was I was writing these equal signs like this. And somebody got confused because they thought that I was working on the right side. Like I had said, oh, this equals this. I was like, no. I was doing that. This equals this, which equals this, which equals this. Oh, by the way, that was the right side, and I'm done. Okay? What do you think about using your reciprocal and quotient identities to simplify and prove things are true? Not bad, right? That one's easy money. That one's easy money. That's why somebody in first period was like, well, how did you know that you needed to say this was 1 over cosine x? And the answer is, well, I see where I'm beginning and I see where I'm ending. Imagine I told you you had to get from school to your house. Is there only one way to get home? No, there's probably lots of ways to do it. And trig identity proofs, there's usually lots of ways to do them. So what is the correct way? Oh, there's no such thing. There's just correct ways. Which one did I choose? I chose what I thought was the easy way. But that doesn't mean it was the only way. And I saw a sine x here, and I know that I was trying to end with sine over cosine. And this sine is already on top of a fraction. It's sine over 1, sine x over 1. So I knew to myself that this left side already has a sine on top, and the right side has a sine on top. So essentially what I needed to do was figure out how am I going to get a cosine on the bottom. Ah, secant is 1 over cosine. How about that? Okay. I know this is a really simplistic question, and you're looking at it and you're thinking, well, how else could you have done it? Well, I mean, there's lots of crazy things I could do, but why bother when there's an easy way? Now, this next example, the author of these notes wants me to decompose this fraction. Decompose means take apart. I'm not a fan of doing it that way. I mean, I'm going to show you what it looks like because it's what I did in second period. But you know what? I don't want to do it that way. There it is decomposed. Essentially what we did was we said, because I have two things on top separated by addition or subtraction, I could write this as two fractions separated by addition or subtraction. They just have a common denominator. So you end up with sine x over cosecant x minus cosecant x over cosecant x. But this is a reciprocal function. So dividing by 1 over sine x is the same as multiplying by sine x over 1. You know, keep, change, flip. And cosecant x over cosecant x is 1. So sine x over 1 times sine x over 1 gives me the sine squared x minus 1 that I was needing. That's decomposing the fraction. I don't want to do it that way. I don't like that, because that's not what I would have seen to do first. There's nothing wrong with it, and clearly it works, right? And what I'm about to do isn't any easier. It's just what I would have done first, because it's just the way that I think. So Adi, I'm about to move it, okay? Here's how I would have done this. Again, I'm only working on the left side. And why am I turning the left side into the right? Because the left side looks like it's got more crap going on. The right side looks like it's been simplified, doesn't it? Oh, by the way, someone in second period instantly recognized that this could have been simplified even more. Oh, it's almost cosine squared x. Cosine squared x is 1 minus sine squared x. This is backwards. So it's negative cosine squared x. But we're going to leave it like this because this is easy to get to. But realize this could have said equals negative cosine of squared x. It could have. Here's what I would see. I notice that the bottom of this fraction is a reciprocal function. So instead of dividing by cosecant of x, that's the same as multiplying by sine of x. I'll write it out. Because when dividing by a fraction, you could actually multiply by the reciprocal. You could keep, change, flip. So instead of dividing by 1 over sine x, I could actually multiply by just sine x. And distribute the sine x. When you distribute the sine x, and by the way, say this is, I'm working left side only. Okay. When you distribute the sine x, what you get is a sine squared x minus cosecant x times sine x. What relationship do cosecant x and sine x have? No, not inverses. They're reciprocals. What do you get in mathematics when you multiply two reciprocals? 1. How about that? Done. Because they're reciprocal functions, multiplying them to each other results in 1. So is decomposing the fraction any less work? Any more work? No, it's just different. I don't like doing that. Like this one. I could decompose this fraction, but it would require me to know the Pythagorean identity for sine or for secant squared x. And guess what? I don't know it. So, I mean, I could flip the paper over and take it off the front. I could. There it is. So I could say the top of that fraction is 1 plus tangent squared x if I wanted to, and then I could decompose it. But since I don't know that identity by heart, that would not be the way that I would have approached it. Instead, what I would have done is looked at what I have and looked at what I need. This has 2 secants in the top of this fraction, doesn't it? This side has 1 secant in the top of its fraction. Because I already have secant in the top of the fraction and I know I want secant to stay in the top of the fraction, I don't want to manipulate secant. I want to keep secant. But that's just a me thing, okay? That's what I see. I see I needed secant on top and it's already there, so I want to keep it there at all costs. So instead of saying secant squared x, what I'm going to say is secant x times secant x. And instead of saying that I'm dividing by tangent of x, I could multiply by cotangent. But whoa. Multiplying by cotangent is weird. I mean, what is secant x times cotangent x? I don't know. But I tell you what. Remember what tangent x is? tangent x is sine x over cosine x. So instead of dividing by sine x over cosine x, I could multiply by its reciprocal. And why would I have wanted to do that? Jack, you said this was way more complicated?
No, I did it.
But you did it in an equally correct way, didn't you?
Yeah,
Yeah, well, there you go. You see, it doesn't matter. But I like doing it this way because secant and cosine are reciprocals. And when you multiply reciprocals, you get 1. What that leaves me with is secant x times 1 over sine x. Oh, by the way, 1 over sine x is cosecant x. Now, if you would like to see it decomposed, doing that method, I can show it to you. So that way you could see what that would have looked like. But do you have questions about how I did it? Have you noticed that if I hadn't told you where this came from, that it might have been kind of a stretch for your brain just looking at it to go from here to here? You might want to write a lot more things down than just the math. You might want to write yourself some explanations as to where things are coming from and why we did them. Okay? Here, don't worry, it'll come back, is what it looks like if you turn secant squared x into 1 plus tangent squared x. So there's the 1 plus tangent squared x decomposed to here. 1 over tangent x is cotangent x. Tan squared over tangent, that's just tangent x. Then what you have to do is say cotangent x is cosine over sine. Tangent is sine over cosine. And in order for you to add two fractions, you need a common denominator. The common denominator then must be cosine times sine. So you multiply the top and bottom by cosine x, which just squares that top. You multiply the top and bottom of this one by sine of x, which just squares the top. It combines to one fraction, but cosine squared x plus sine squared x is the Pythagorean identity, which equals 1. And 1 over cosine is secant, 1 over sine is cosecant. That is the way that the author intended for us to do that question. But I don't like it. I prefer that. Are there times when you can't avoid adding and subtracting fractions and finding common denominators? Of course there are. But this was a time where I could avoid it, so I chose to avoid it. There was no subtraction or addition in the result. Why would I introduce subtraction or addition if I don't have to? So I just stuck with all multiplications and divisions, because that's the way I think. I freaking love this material, because it's the only material that I teach you this year, or that I've taught you this year so far, where I don't look at it and instantly know what the answer is. I look at this stuff and go, okay, let's see how I'm going to do this. And there will be times, there's a good chance there's going to be times where you see me try and get stuck and go, well, that didn't work, let's try something different. Because I don't have the answers in front of me. I mean, I could open them, but why would I do that? I'd rather challenge myself. Again, trying to prove that this is a true statement. Look how simplistic the right side is and how complex the left side is. Remember, you are allowed to look at where you're headed and think about how to get there. This right here is sine over cosine, correct? My left side already has a sine on top. So our job is to figure out how we're going to get a cosine in the bottom. Oh, secant! Secant is 1 over cosine. And also, this we said is sine over cosine. It only has a single sine on top. Where'd this other sine go? See, these are questions you're asking yourself. And then you go, oh, wait a minute. Cosecant. That's 1 over sine. So working the left side. instead of saying times 1 over, instead of saying times secant, I could say divided by cosine. And instead of saying times cosecant, I could say divided by sine. Oh, by the way, sine theta divided by sine theta is 1, and sine theta over cosine theta is tangent theta. How about that? So this, I could have written this out like this. But that just puts these two things in the denominator, which is what I had here.
You see, as long as these both are the same thing on both sides, it doesn't matter.
What do you mean? So I didn't do any, I didn't do an operation to both sides, if that's what you're asking.
Yeah, like if I ended up with sine squared theta over cosine theta times sine theta on both sides, that's fine.
Yeah, if you manipulated this side independent of this side, and you manipulated this side independent of this side, but they both equal the same thing, you're set. Yep. For like, yeah, what did you do? Did you just multiply the top and bottom by sine theta right here? Yeah, because that's, you could do that. So if you said this is sine theta over cosine theta, and you multiply the top and bottom by sine theta, you get sine squared theta over sine theta cosine theta, and this is sine squared theta over sine theta cosine theta, done. Yep. Because that was doing things on either side independent of one another and getting that they equaled the same thing. That's how you did the last one too? Yeah, and you're completely allowed to do that, 100%. And like I said, I was doing the homework questions just to see what you guys are going to have to do. And one of the questions, that's actually how I did it. I was like, yeah, I think I'm just going to work both sides of this until they equal each other, because it looked like less work to me. How did I know to do that? Well, again, like I said, I looked at this and saw how simple this side was. So if one side is already really simple, I typically will just try to get to that simple version. If both sides are hideous, I might just try to work both sides independent of one another and hope, you know. Let's see what's going on. Oh, crap. All right, we finally have to deal with this plus or minus, right? We have addition and subtraction. I'm not going to be able to avoid it. So let's look at what we have and look at where we're trying to go. I'm trying to end up with a 1 over cosine of x. Ooh. Tangent of x is sine x over cosine x. So right here is my bridge. This already gets the cosine into the denominator that I needed, doesn't it? Okay. So how about I write this as sine x over cosine x? So I'm just working the left side. This gets me sine squared x over cosine x plus cosine x, technically over 1. Wouldn't it be nice if they had a common denominator? It would be, right? What's the common denominator? Cosine x. This one already has cosine x, so that fraction I can leave alone. This one I'm going to have to multiply the top and bottom by cosine x. But since there's already a cosine x on top, when I multiply it by cosine x again, I just get cosine squared x, don't I? But now that they have a common denominator, I can write this as one fraction. Sine squared x plus cosine squared x all over cosine x. Do you see it? What am I talking about? The Pythagorean identity is 1. This equals 1. That's the Pythagorean identity. So once again, I worked only on the left side and eventually got to the right side. Finding common denominators is going to be a very useful tool in your trigonometry proof toolbox. Always on the lookout for sine squared x plus cosine squared x. Remember, order of addition doesn't matter. So cosine squared plus sine squared, it's the same thing. Okay. Equals 1. Always on the lookout for that guy. Do you have any questions for me about manipulating these things to show truths? No. Okay. Then let's flip it over and see what's next. Because that's as far as I made it with period 2, because they don't ever stop talking. Here we go. Ah, yes. Look at this thing. Look how fun this looks. Look at all the space we have. Okay, well, let me tell you what you don't have. You don't have any squared trigonometry. That means the way it sits, you have no Pythagorean identities. All of the Pythagorean identities require squared trig. It's required. Mr. M, isn't this tangent? It sure is. But I'm going to be real with you. I don't see how that would help you. Mr. M, can I decompose this fraction? No, you cannot. You cannot decompose this fraction because the bottom has two things in it that are held together, pluses and minuses. You can only decompose when it's the top. No, this is not cosine squared because this is not 1 minus sine squared. And that's why I said we have no squared trig, so we can't do any Pythagorean identity stuff. But what would you have to do to make it say 1 minus sine squared theta? If I multiply this by sine theta, or x, excuse me, I'll get sine x minus sine squared x. We want 1 minus sine squared x. 0 over 0, don't you dare. She's trying to break the universe.
Wait.
Remember when I told you that a lot of the Pythagorean identities are the difference of two squares? That always factor to conjugates? This factors, doesn't it? What does it factor to? 1 minus sine theta times 1 plus sine theta. Not both sides. You can't do anything to both sides. But you can multiply the top and bottom of this fraction by the conjugate. 1 plus sine x. I can multiply to the top and bottom of a fraction because this is just 1. I can't multiply to both sides of an equation because that assumes it's a true statement already. Realize that right now I'm only working on the first fraction. Okay? Let's see what this gets me in that first fraction. It gets me cosine x when I distribute plus sine x cosine x. Yes? On the bottom, it gets me 1 minus sine squared x, which is cosine squared x, right? You know what I shouldn't have done? I shouldn't have distributed. I just realized that. Oh, wait. Yeah, I shouldn't have distributed. If you don't mind, I'm going to factor it. Might be. I shouldn't have distributed on top. I shouldn't have distributed on top. Just go with me, okay? Because I'm seeing now that I shouldn't have. And here's why. Now my two fractions have the same denominator. Where did what come from? I didn't memorize anything. What are you talking about?
1 minus.
I said I have that memorized by accident. Okay, but the moment you have squared, like it helps. It helps. By the way, this is not the only way to do this question. You could have just found the common denominator right here. That works also. Look, I know. I said I know those two Pythagorean identities by accident. I said that. Anyway, that gives me 1 plus sine x over cos x minus sine x over cos x. They have the same denominator, don't they? So when I combine this into one fraction, it gives me 1 plus sine x minus sine x over cosine x. And sine x minus sine x is 0. I get 1 over cosine x, which is secant x. So for those of you that are complaining that the only reason why I was able to see that is because I do have a Pythagorean identity memorized, you're not wrong. So instead, what you could have done was multiply the top and bottom of this by cosine x, multiply the top and bottom of this by 1 minus sine x. Be very careful when you distribute your negative sine x. And when you do that, a bunch of stuff on top will combine and cancel the stuff on the bottom. And it will work out. You know what? Maybe do that one at home the way I just said. Just to see it. That way you can see that you don't have to be a big power nerd as me and know the Pythagorean identities.
That